Hi. I already introduced myself yesterday, but anyhow, I'm Tzahi from Mellanox, and I would like to talk today about RDMA and user space Ethernet bonding. Um, okay, so the agenda would be first I'll start with a quick introduction. I'll discuss what is NIC teaming, how basically it relates to the Rocky and the IB device, and how IB device and NIC teaming are related. And within the introduction, I also show how this is reflected to the application from the application point of view. Then I'll show our RDMA device hardware bonding support and how we enable it. Then I'll continue to show how this applies to virtualization, what's the software model for virtualization, and how the embedded switch for SRARV can support bonding as well. I will finalize with a nice twist for the hardware bonding capability with the MULTI-PCI socket NIC. I'll explain what is it and how the bonding is being used there. Okay, so what is teaming? So basically, IEEE .3ad defines how to combine multiple physical ports into a single logical port. The purpose is to provide high availability, so traffic can be spanned across those ports, and also to support load balancing. So whenever a port fails, traffic can transparently revert to the other port. In Linux, this is being used by the bonding or the new teaming device, which allows you to build basically a link aggregation trunk. Both of those bonding and teaming models expose basically a software network device. It provides a link aggregation net device to the stack, and basically enslaves the actual net devices that associated with the actual physical ports. The teaming device is considered the upper device, and the slaves are the lower devices, which are enslaved. Basically, what is exposed to the stack is the logical device. It has an IP address, it has transport properties, and the lower devices are basically left for merely physical port management. So you can do eth_tool and stuff like that. There are different modes of operation supported with link aggregation. There's active-passive, there's active-active with static lag, and with dynamic lag or link aggregation control protocol, where the difference is that with LACP, you configure one side, the switch side, and the other side is being configured automatically through the LACP protocol. Now, next one is the RDMA device. So, what is the RDMA device? Basically, as we know, there's three RDMA stack protocols that are generally supported: the Rocky, the InfiniBand, and the iWarp. Rocky basically defines how you encapsulate RDMA InfiniBand headers on top of UDP. In Rocky, we basically use IPv4 or IPv6. We support both. And we use basically the addresses that were assigned to the network OS stack interface. So those are basically the IP addresses of the Linux NetDev. Rocky application use RDMA CM API for control and Verbs API for data path generally. Just a quick recap: what is the RDMA CM and what is Verbs? So basically, RDMA CM provides address resolution functionality, route lookup, path lookup, connection establishment, and Verbs allows to do the actual data path operations, send RDMA, poll for receive with asynchronous completion, and posting receive buffers. All of this is being exposed through a new device, the IB device. That's the RDMA device. And the RDMA device with Rocky is associated with the network device, where it uses its IP addresses, its MTU, and such transport properties. When I'm saying Rocky, I would like also to mention that it also applies for user mode Ethernet. So with Verbs, where you have IB device, you can either do Rocky or you can do user mode Ethernet as you've seen yesterday. One example is DPDK, who uses the Verbs to implement the API. So how is that connected? So basically, as we see in the slide, if we look at the TCP/IP stack on the left side, we can see here that here we have the NIC or HCA. We have two ports that the NIC exposes through two network devices towards the stack. Those devices are lagged or bonded through the Linux bonding module. And on top, we see a single network device as described that is exposed to the stack. Single IP. The stack uses this IP. On top, there's the socket layer and then the application. So basically, whenever you instantiate a socket in the application, such socket transport object has all the control facilities and all the management in the TCP/IP stack in software. So basically, whenever this module introduces a change, if there's a link down, if there's any LACP change in the bonding configuration, the upper layers don't really care. We still see a single interface, single IP, nothing changed. So we would like to get such functionality also for RDMA. And for RDMA, we see here we have the Verbs application, we have user Verbs, and basically we have direct hardware OS bypass API that can communicate through user mode to hardware directly. So we can see here we have the QP object, which is the transport object similar to sockets, but this object is being managed in hardware. So all the transport is being managed in hardware, and that's why we do need hardware assistance to support seamless link aggregation for Rocky or for user mode Ethernet. So how we do that? So basically, the idea is that we register a new IB device. We associate it with the bonding device over here. So if we look at the diagram, we can see here the NIC, the two physical ports. There's a hardware band logic that I will explain soon. We have here the two PCI physical functions. We have two NetDevs, the OS network interfaces. We have the RDMA devices on each one of them. And whenever we basically trunk those NetDevs into a single Linux bonding teaming device, we actually negate those interfaces from the IP, from the network stack, and expose a new software-based NetDev. So we suggest also to register a new RDMA device. So basically, we will listen in ETH0 and ETH1 on netlink events and detect that such an association was formed. And in reaction to that, we'll detect what is the upper net device and associate it with a newly registered IB device. Whenever there's such an administrative change, which is basically a very big change, you take the IP addresses from those interfaces and associate them and create a new network device. So this is a big change, and in terms of active consumers on Verbs, we feel it's practically okay if we basically cease to service such consumers and ask them to basically re-establish the hardware resources on top of the new IB device. So we basically unregister and re-register those IB devices. And why do we need those? Similar to those network devices, in order to basically manage the physical ports. So we can use the IB device tools to still manage the ports, not transmit any or receive any data, only for management. Now, going to the hardware bound logic and what is the purpose of this module. So basically, this model needs to allow seamless operations of passing traffic from the physical port to the transport object, or from the transport object to the right physical port. So there's a very important logic here. So we keep, whenever we assign a transport object to a port, it always uses this port for both ingress and egress. And for network traffic, we must use this port, so these interfaces. So whenever network traffic or traditional TCP/IP traffic comes from this port or this port, we would like to use the traditional PCI functions, and through that get to the traditional network devices. So traffic remains the same as if it wasn't an RDMA device. It's important since even when, for LACP especially, even when a port can be administratively down, we still need to pass the LACP traffic through that port. So if LACP traffic goes here and this port is considered administratively down from bonding perspective, still traffic needs to pass through here and come to the Linux bonding through here for proper logic of this model. In terms of failover, both RoCE and user mode Ethernet that use the QP in the hardware, the transport object in the hardware, needs to migrate transparently. So basically this logic, whenever there's a failover event, this logic basically migrate the transport object, the QP, either if it's a RoCE or if it's a user mode Ethernet, into the active port. And as I mentioned, traditional network device traffic remains associated with the actual slave network device. In terms of the Verbs API, we basically added a new QP attribute, port affinity. So whenever there's an application running here and this application would like to choose or would like to have control, we have customers that would like to have control which actual physical port is being used, but the application here sees a single physical port from its perspective because we have a trunked port. Then we've added an attribute we called port affinity or entropy, that you can give the hardware a hint which physical port you would like to use. It's not a mandatory attribute, it's optional, but basically customers would like to use that so they can better load balance the ports. If they detect that one port is too busy, then can create new transport objects on top of the other port. So in terms of configuration, as you can see, it's pretty much uses the standard Linux configuration. You use the standard Linux tools to form this object and slave those network devices. And by listening to those netlink events, we basically allow RDMA functionality and registration of the new RDMA device. Regarding the LACP protocol itself, so there are basically two options. The LACP protocol can run here in software in the Linux bonding module. And the other options would be to run this LACP protocol in hardware over here. So basically, if you have a multiple PF to physical port, multiple physical function to physical port configurations, so many network devices are associated with the same physical port, you would typically use an LACP protocol that is running in hardware. So how this applies to virtualization? So in virtualization, SRIOV, we basically have an embedded switch inside the NIC over here. So I would like to show how basically this technology is being used for the embedded switch, and how we basically trunk ports of the embedded switch in the NIC and allow RDMA bonding as well. So how we basically characterize the embedded switch in terms of software, in terms of Linux modules. So we can see in the slide here, we have the embedded switch here. Those are SRIOV VMs, and those are para-virt VMs, VMs that run on a virtual software switch. There can be a mix of them, and this is what I show in the slide. So the architecture that's supported is that for those SRIOV VMs, we basically expose representer network devices in the hypervisor. So in the hypervisor, in this setup, we basically see three network devices, one that represents the physical port, and two that represents the virtual functions, the vPorts. All of these three ports are enslaved with the Linux bridge or the OVS bridge. The OVS bridge exposes a software-based network device, the BR0, which is used for the native OS, for the hypervisor stack for networking. And the VMs, the para-virt VMs, are connected directly to the Linux software switch. So basically, how traffic flows, if an SRIOV VM would like to send traffic, it is being sent by the vendor driver over the virtual function in the VM directly to the E-switch. The E-switch performs the forwarding. If it's outside, it goes to the physical port. If it's inside, it goes to the ETH0, which represents the physical ports towards the hypervisor, then through the virtual switch in software, and the virtual switch will do the forwarding either for the hypervisor or for the para-virt VMs. For para-virt VMs, we always go through virtual switch and perform software-based FDB, and either talk to each other or talk to the native OS. That's basically one option. The other option that we can support, you can see here quickly the difference. The difference mainly is how the native OS or the hypervisor is connected to the embedded switch or the virtual switch. In the previous configuration, we can see that the native OS is connected through the software switch. So basically, whenever the hypervisor wants to talk to any VM, it must go through software forwarding database first. If it's local para-virt, then that's it. If not, it needs to go to the embedded switch, and then again forwarding either to SRIOV VMs or to the wire. In this configuration, the hypervisor port is also considered first-class citizen in the embedded switch. So it basically gets a direct queue to the embedded switch. All traffic goes first to the embedded switch. If this traffic needs to go up to the software switch for the para-virt VMs or for any slow path traffic manipulation, then it has its own representer in as a different separate queue. So traffic may go to the NIC and go up again to the representer and then go to the virtual switch for software-based forwarding or packet manipulation. So these are mainly the two options. How this relates to bonding? So basically, in this slide, we can see how bonding fits in. So we can see here that we still use the standard Linux bonding. We actually bring up the bonding with enslavement of the actual physical port representers. So we are using the same model as before, but in this case, the port that we associated with the Linux bridge is the port that is exposed by the Linux bonding module. So it fits very nicely with the virtualization model, where for paravirt VMs, software-based forwarding is done directly to the Linux bonding. Linux bonding does the hash and goes through the right physical port. For egress traffic from the VMs, for ingress, the same, based on the logic I explained before, by the hardware bond that passes up the traffic through the right representer ports. For the VMs, it's pretty much transparent. The VMs see a single port, a single net device. This net device goes to the E-switch. The E-switch has a similar hardware bond, as I explained in the other slide. So basically, the VMs enjoy the link aggregation functionality pretty much transparently. And as well as the native OS, which also either uses the virtual switch in option 1 and uses the Linux bonding to send the traffic, or through the E-switch and the hardware bonding directly. This is just a quick slide to show that we can also support tunneling in this model. And we have here basically the VXLAN net device in this example that exposes a VXLAN VNI interface. So basically traffic that needs to go through encapsulation or decapsulation goes from the Linux bridge into the bridge that represents the tunneling network, into the tunneling interface, and then into the E0, into the NIC. Of course, a NIC that supports also hardware-based encapsulation, decapsulation communicates with this module and initialize correctly the hardware tunnel module as well. And since we are using same software model, same tools, basically bonding can fit right in this diagram and also can be supported. Another topic and the use case for bonding is basically a nice feature, the MULTI-PCI socket NIC. So what is a MULTI-PCI socket NIC? So basically, it's a technology where a single network device can be connected through two different PCIe buses. In this example, we show that a single network card is connected through two PCIe by 8 wires. Each PCI bus is basically connected through different NUMA node. For the operating system, it's basically exposed through two different network devices, two different PFs. And in this way, applications can enjoy local NUMA access from any one of those cores. So application can choose if it runs on this core, it can send and receive traffic through this lane, and if it runs on this core, it can send and receive on this lane. And doing so, it basically can bypass the QPI bus. So we can see a nice performance boost. I will show some graphs next. Also, a nice use case is to enable GPU-based peer-to-peer applications or solutions to work from both PCI slots. So you can do peer-to-peer over this one and over this one. And another nice advantage here is that you can enjoy the DDIO technology from both NUMA nodes. So basically, DDI technology where you can access the cache, the local NUMA cache directly. You can access it from here and also from here. So whenever there's, typically if you pass to the QPI, you don't enjoy the DDIO technology, and in this case, we enable it. So some benchmark numbers in the slide. We can see here, basically, we ran a simple test, netperf, with 300 TCP connections. So we divided those connections on top of 2 NUMA cores. So you can see in red the average latency without socket direct using a single NIC. One NUMA node is local and the other NUMA node is using a remote device and passing through the QPI. And the green one shows whenever we use it with socket direct. We can see here a nice latency drop by 20%. And in terms of CPU utilization, we can see a very nice improvement as well. Basically a 50% CPU overhead drop. So in this slide, basically I show how we can use the Linux bonding model and the technology we built with RDMA device on top to support such a configuration seamlessly. So as you probably seen, in order for application to use this technology, this application needs to be aware of 2 network devices. It needs to control which traffic is being sent to which. You have 2 IP addresses on your machine. It can be inconvenient for some applications. So here we can show that we can support such technology also with a single IP, with a single network device that is exposed to the stack through the Linux bonding. So we basically suggest to form the Linux bonding on top of those 2 devices that are associated with the 2 physical functions. Here we have the hardware bond, and we have here a single physical port, again, since we are using 2 PCI buses to expose a single NIC. So how traffic flows for TCP, basically we have select queue logic. So select queue logic select the right queue from ETH0 or from ETH1. By selecting the queue, we actually know which PCI device should be sending the traffic. So we can choose the right device, the right local device to send the traffic. For receive, we basically use a technology that Linux supports, the accelerated RFS, where basically the Linux stack educates the NIC which tuple needs to go to which queue, to which receive queue, based on the socket send and the socket receive CPU locality. So basically, whenever there is a receive, we do a match on the 5 tuple, and we know which one of the legs should be chosen for passing the traffic up the stack. For RDMA, as I mentioned before, we have the transport object. So either we do it explicitly, the transport object can specify its affinity, which CPU it uses, and then we use the right physical functions to create this QP and to send and receive traffic on this QP. By dividing the QP numbering range between those 2 legs, we basically can know on receive path which leg should get the traffic. Last but not least is to mention that you basically can't share the objects, share transport object or share RDMA object between those legs, since each one of them has a different namespace. So if you create a CQ that is affinitized to this leg, you can't use it with a QP that was affinitized to this leg. And this is okay, since the whole purpose here is to bypass the QPI. Okay, so to summarize, we saw that transitional stack transport logic is managed by the TCP/IP stack, and with RDMA devices, basically the transport is being managed by the hardware. So we need to create a kind of a control path where the hardware is aware when there is a bonding being formed and when there is a failover and migration event that needs to occur. We see here that building a solution based on existing infrastructure, we can provide a pretty much seamless administrative and application-wise configuration. Application sees a single interface like a socket API. And we can also allow hardware to be aware of failover event and transparently move the hardware objects to the active port. And in the last part, we basically saw that we can use the same logic with multiple logical devices mapped to a single physical port for getting performance and for enjoying UPI bypass. That's it.
So are you guys doing the link bonding for the RDMA in the hardware, and the software you have option to do it in the hardware or in the Linux?
We're doing it in hardware and
basically when you're doing the link aggregation, I'm talking about link aggregation, not the PCI link sharing, but link aggregation, for the RDMA traffic, is it done in the hardware? And for the Ethernet traffic, it can be done in the Linux or in the hardware. Is that correct?
Yes. So basically what I've shown here is that for the TCP/IP traditional traffic, link aggregation and hash and which traffic goes where is done in the Linux bonding module. This was important to some customers because they wanted to control which port is being used and load balance accordingly. And for RDMA, obviously the transport object is in the hardware and bonding needs to be done in the hardware only.
And what kind of hashing you're using for RDMA traffic?
What kind of?
What kind of hashing?
Hashing.
Yeah.
So for RDMA, there's no hashing.
Yeah.
You use a QP attribute, the entropy or the affinity. Whenever you instantiate the QP, you can modify it dynamically if you want to, but you need to do it by the application logic. And it is being modified automatically whenever there's a failover event.
And both the port has to be part of same controller. Is that correct?
What?
When you're doing the link bonding, then both the physical port has to be part of the same controller, because you have hardware bonding.
It has to be part of the same switch?
Same switch, yeah.
So not necessarily.
Not necessarily.
You can create a link aggregation group in the same switch, but you can also use technologies like MLAG to do it between separate switches. So both are supported.
So you will support two different switches as well?
Yes. Practically, we don't really care. Once we see a link aggregation group and we see switches that comply to the 3AD link aggregation spec, we don't really care. So there's a technology called MLAG that can support that in different switches.
Got it. Okay. Thank you.
Okay.
Not really a bonding question, but about embedded switch. There is a standard called QBG. Do you do it?
QBG?
Yes, 802.1 QBG about the VEPA type of port aggregators.
Yes. Well, yes, it's not related to the bonding. This is not something that is supported in current version, but indeed in our roadmap, and we do support VEPA mode like embedded switch. So you would like all the traffic to go outside and not loop back internally, yes. We already support it in our previous hardware, the ConnectX-3, and the new hardware, it's supported in hardware, and software support will be released later on, but yes. That's it. Thank you.